Welcome back, everyone, to MAE170. This is lecture 7 in week number 4. So before starting with the actual topic for lecture 7, let's go back a little bit to lecture 6 because we have to finish what we haven't covered. And before doing that, I just want to give you a quick review of what we saw last time. So when we design a control system, we design the control so that the system performs in the way that we want. What does that mean? We want the output of the system to match certain requirements. So how do we translate these requirements into maths? Well, first of all, we have to take into account that a system can be of different orders. It can be a second order, first order, second order, third order, fourth order, so on and so forth system, depending on its poles. And furthermore, the system can be subjected to different kinds of inputs. So how do we define the requirements and the performance indices? Well, there's a standard for it, and the standard is to consider a second order system and a step input. And so we define the performance indices according to the response of a second order system to a step input. Furthermore, the second order system is also thought to be underdamped so that the response looks exactly like what we saw last time, this green curve over here. And so based on this curve, we can define the peak value, MP, the time at which this value occurs, that is the peak time, and then based on the final value, the overshoot or the percent overshoot more often than that. The rise time, we have two definitions for the rise time. The more general considers the time that it takes for the response to go from 10% to 90% of its final value. Then the settling time, and finally, well, we can consider the final value itself and the steady state error. All right, this is all nice for a second order system that is underdamped. But what if we had a system of order greater than 2? Well, in this case, let's go down. There we go. So how do we define the system performances if the system is of order greater than 2? Well, let's take a look at an example to understand how we can proceed. Because in the end, we have to use what we've defined. Otherwise, that was all work for nothing. We defined all the performance indices referring to a second order system. So somehow we have to use those and try to approximate higher order systems to second order systems. Sometimes it can be done, sometimes it cannot be done. So let's see when it can and when it cannot be done. So let's take a look at this fifth order system. Fifth order system implies that we have 5 poles. So let's say that we have P1 and P2, that is pole number 1 and 2, at -1 and minus plus 2i. So P1 and 2 are complex conjugates. And let's place them on the S-plane here and here. Then we consider a real pole at -2. So once again, let's place that. And finally, the remaining 2 poles are also complex conjugate at -3 minus and plus I. So before proceeding, let's try to see if these poles are even possible for a control system. So the control system has a transfer function that can be written as a fraction with the numerator and the denominator, and both numerator and denominators are polynomials with real coefficients. So in this case, we're looking at the poles, that is the roots of the characteristic equation, that is d of s equals 0. So since the polynomial has real coefficients, according to the fundamental theorem of algebra, its roots must be either real, like P3, or if complex, like P1, 2, 4, and 5, they have to be complex conjugate. P1 and 2 are complex conjugate, and so are P4 and P5. So these 5 poles can represent the poles of a system. Okay, so always make sure that what you're given makes sense. All right, so let's name that. Now, if we were to take the response of the system, selectively breaking it down to the contribution of its poles, we can consider the complex conjugate poles response together, so P1 and P2, and then P4 and P5, and then P3 alone. And why am I doing this? Well, that's because what really matters is the real part of the poles. The imaginary part of the poles will just contribute to an oscillatory behavior, a sinusoidal behavior. But it's the real part of the poles that will contribute to either an exponentially decaying response or an exponentially increasing response. That depends on the sign of the real part. If the real part is negative, then the contribution is going to be exponentially decaying. The imaginary part, let me repeat once again, just contributes to an oscillatory behavior. So it does not really die down with time. What dies down is just the exponential if the exponent is negative. In this case, all the real parts of P1 through P5 are negative. So the exponential behavior connected to these poles is proportional, when we take a look at P1 and P2, that is proportional to e to the power of the real part of P1 and P2, that is -1 times t. Then for P3, the response or its contribution to the response is proportional to e to the power of, well, its real part, which is -2 times t. And finally, for P4 and 5, we have that the contribution to the response is proportional to e to the power of -3 times t, being -3 the real part of both P4 and P5. Now you see that all these contributions eventually will go to 0, because as time increases, e to the power of minus something that increases just goes to 0. But e to the power of -1 times t goes to 0 a little bit slower than e to the power of -2t. And then e to the power of -2t goes to 0 more slowly than e to the power of -3t. And of course, e to the power of -1t is slower than the third one. Here, you can also look at it the other way. So as the time increases, e to the power of -3t goes to 0 faster than e to the power of -2t. So it's just looking at the other way. And e to the power of -2t goes to 0 faster than e to the power of -t. In other words, the response associated with P1 and P2 after a little bit becomes dominant because the response associated with P3, P4, and P5 has already died down. So P1 and P2 contribution to the overall response is dominant. And in this case, in fact, P1 and P2 are known as the dominant poles. So if you have a system that has more than two poles, well, the dominant poles are the poles that have the real part that is smaller in magnitude. Of course, I'm considering systems with all poles with negative real part. And because if you had poles with positive real part, then the contribution, the output will just blow up to infinity. And the system would be known as unstable. And that's what we're going to see later on today. So we definitely don't want poles with positive real parts. So if all the poles have negative real parts, then the dominant ones are the ones closer to the imaginary axis. So in this case, P1 and P2 are the dominant poles. All right, so you see that we have P1 and P2. They are dominant. So let me repeat once again, that means that their contribution to the overall response is dominant with respect to the response or the contribution of the other poles. So we can think about maybe neglecting the contribution of P3, P4, and P5 and just focus on the contribution of P1 and P2. Well, you see, we have P1 and P2, second order system. But wait a minute, we've just studied that we've defined all the performance parameters for a second order system. So why don't we use P1 and P2 to calculate all the performance parameters? Well, and that's exactly what it is done. So how do you do that? Well, P1 and P2, let me write it again. They're equal to -1 minus or plus 2i. And so what you can do is you compute the natural frequency and the damping ratio associated with these two poles. How do you do that? Well, P1 and P2, if they were just related to a second order system, and that's the kind of the approximation that we're doing, you can also write them as minus zeta omega n minus or plus I square root of, sorry, forgot, omega n square root of 1 minus zeta squared. So all you have to do is equate -1 with minus sigma omega n, and omega n square root of 1 minus sigma squared equated to 2 in this case. And so now you have two equations, two unknowns, and you can find zeta and omega n. Oh, well, now that we have zeta and omega n, we can calculate all the performance parameters. So now we have the damping ratio and the natural frequency associated with the dominant poles, P1 and P2, can be used in order to calculate the percent overshoot, the settling time, the rise time, the peak time, and the peak value using the formulas that I provided you previously. Very nice, right? And that's exactly what it is done. Sometimes you won't have exactly a pair of dominant poles. Let me give you an example. If we had a third order system, well, third order system means that we have 3 poles. So let's say that one pole is over here, and then the other 2 are here and here. Well, in this case, the dominant poles, well, it's actually the dominant pole. It's only one, because this one is closer to the imaginary axis. So in this particular case, it's a little bit more tricky. We cannot really do that because definitely this pole here does not have a damping ratio and a natural frequency associated with it. However, if we had a third order system that looked like this, so if the 2 complex conjugate poles were more to the right with respect to the real one, well, in this case, we could use the complex conjugate poles to find the damping ratio, the natural frequency, and indeed use the performance indices as defined previously. You can always define the performance indices even for a system like this with just one dominant pole. The thing is that you would have to take a look exactly at the output of the system, and you cannot estimate the performances using the equations that I provided. That's the only drawback. All right. With that being said, let's now take a look at an example. And this is exactly the effect of the third pole. So if we had a second order system defined as usual with omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So this would technically be a second order system. But if we added a third pole, well, this pole must be real because we already have 2 complex conjugate poles, while the third one has to be real. Again, because of the fundamental theorem of algebra. I have to repeat it ad nauseam. Okay, so now we want to know whether or not this third order system can be approximated, or if its behavior can be approximated with the behavior of a second order system. You cannot really approximate a third order with a second order, but the behavior, or that is the output, might be similar. All right, so in this case, we have, as I said, the first 2 poles, P1 and P2, always as minus sigma omega n minus or plus I omega n square root of 1 minus zeta squared. And the assumption here is that these 2 are closer to the imaginary axis, that is, they act as dominant poles. And then we're going to have our third pole at minus sigma. And we're going to have this real part more negative. So P3 is more to the left with respect to the pair P1 and P2. Now here there's a rule of thumb, and this is the following. If the real part of P3, that is, or if the magnitude, I should say, of the real part of P3, that is absolute value of sigma, is greater or equal to about 10 times the real part of the dominant poles, then the effects of P3 are pretty much negligible. All right, so if, for instance, P1 and P2 were minus 1, well, plus or minus I2, and P3 was equal to minus 13, well, then you can take, even without computing the actual output, you know that the output or the response of this third order system is pretty much equivalent to the response of a second order system having P1 and P2 as its poles. Well, sometimes, even if you had not exactly 10, but maybe 5 or 6, you could also approximate the response of a third order system with the second order system. We don't always have the luxury of having the third pole so far to the left. So with a little bit of experience, you'll see then in practice whether or not you can actually approximate a third order system response with the second order system. So in case you can actually neglect the presence of the third pole, well, somehow you cannot really do that, or you have to be a little bit careful. And this is because of the following reason. Or better, I should reword what I just said. If you wanted to just consider a second order system that behaves similarly to your third order system, given that this condition is met, then the second order system that you have to consider is not just the standard omega n squared divided by, s squared plus 2 zeta omega n s plus omega n squared, but you have to multiply that, you have to rescale it by 1 over sigma. And this is because if you didn't do that, the final value would not be the same. And let me show you what I mean with that. So let's consider a step input. So R of S is equal to 1 over S. Therefore, the output of the actual third order system, now let's consider just the third order system, and I'm going to call it Y3, 3 because of the third order, is equal to the transfer function T times the input. And so we have omega n squared over s squared plus 2 zeta omega n s plus omega n squared times s plus sigma, and this is T3. And now we have times 1 over s, which is R of s. So we have another s at the denominator. So what is the steady state value? Can we apply the steady state value? Well, two poles have a negative real part. The other pole has also a negative real part. And the other pole of this y3 function is 0. So multiplicity equal 1. It all works out. So we can apply the final value theorem. So limit for s that goes to 0 of s times y3. Oh, I just wrote it. All right, so if s goes to 0, this goes away, this goes away, this goes away. And so your steady state value is 1 over sigma. Now let's take a look at the response of a second order system with the scaling of 1 over sigma. And I'll show you, and now you'll see why it's necessary. So y2 is equal to t2 times r. And so in this case, we have that everything is almost the same, except for that we don't have s plus sigma, but we have just sigma. So now the steady state value is, well, can we apply the steady state, the final value theorem? Yes, we have two poles with negative real parts. We have one pole with equal to 0, multiplicity equals 1, so that is fine. So the final value is equal to the limit for s that goes to 0 of s times y2. And so goes away. If f goes to 0, this and this goes away. And so we're left with, once again, 1 over sigma. So you see that the scaling of 1 over sigma is necessary in order to meet the steady state requirements. All right, so that is the effect of a third pole, a third real pole. Usually we never talk about zeros. Well, what if we had a real zero? Well, in this case, we can, I'm just going to go a little bit faster here. You see that we've added a real zero at minus a. And remember that the zeros are indicated with circles, and poles are always indicated using crosses. So first of all, we have to scale our transfer function with 1 over a in order to maintain the steady state value. In this case, the two poles are once again equal to minus zeta omega n minus or plus I omega n times square root of 1 minus zeta squared, and then the 0 is real and place that minus a. So what are the effects of an extra 0 to a second order system? Well, as the ratio between a and zeta times omega n increases, then we have that the percent overshoot decreases, the peak time increases, and the settling time decreases. So when can we neglect the effects of an extra 0? Well, that is when this ratio a over zeta omega n is much greater than 1, or when the real part of the 0 is much greater than the real part associated with the poles. So kind of similar to the last case that we saw. The effects of the zeros, in other words, are negligible if the 0 is way to the left with respect to the dominant poles. So if the dominant poles are here, and if our 0 is way to the left, then the effects, and these effects once again are on the percent overshoot, the peak time, and the settling time, can be neglected. And here you can see exactly what I'm saying in this figure, which by the way is figure 5.13 in your book. Here you have responses for different values of the ratio a over zeta omega n. Or you can think about it as we decrease here, the 0 moves to the left. And as it moves all the way to minus infinity, then we're going to have exactly the response that corresponds with the second order system without any 0, which is this curve here, as you can see. All right. So as a summary for what technically should have been last lecture, we have the following. If the system is exactly of order 2, well, then you have 2 poles. Then you can use the damping ratio and the natural frequency of the only 2 poles to compute exactly the system performance indices. Accurate, here I'm using the word accurately, but accurately means really just using the equations that I provided, the formula that we found. In fact, the accuracy per se might not be very high. For instance, if you recall the definition of the rise time, it was just a linear approximation that was valid only for the damping ratio between 0.3 and 0.8. So the accuracy per se might not be very high, but the formulas apply exactly because we only have 2 poles. All right. What if the order of the system is greater than 2? Well, then in this case, you have to locate the dominant poles. And here I wrote that they should be complex conjugate, but I'll show in a second that they might also not be. And then use the damping ratio and natural frequency of these 2 dominant poles to approximate the system performances. Of course, the approximation of the of this higher order system to a second order system gets better and better if the non-dominant poles are way to the left with respect to the dominant poles. Let me give you an example. So let's say that we have a second order system with poles that are located here. Okay, so if you have these 2 poles, second order system, you find the damping ratio, the natural frequency, and you can calculate the performance indices that will describe accurately the response to a step input. Now let's consider instead a 4th order system. And let's say that this 4th order system has 2 poles that are exactly in the same location. But then the other 2 poles are right here. And then we consider another 4th order system with the same 2 dominant poles, but then the other 2 a little bit more to the left. And then finally, a further 4th order system with the same dominant poles and with the other excuse me, with the other 2 poles even more to the left. So all 4 systems share the same 2 poles, these 2 poles, the pair of dominant poles. But the 4th order system that has the poles more to the left will behave more like the original second order system, because the effect associated with the other 2 poles will die down sooner, because once again, the response will be associated with e to the power of the real part of the poles times t. So if the real part is more negative, then the contribution will die down sooner. One more thing, if you had a system whose dominant poles are not complex conjugate, but are real, so let's say that you had 1 pole over here and 1 pole over here, and then maybe other 2 poles here and here. Well, these 2 are still the dominant poles. So you can still use the location of P1 and P2 to find the damping ratio and the natural frequency. How to do that? Well, in this case, since P1 and P2 are real, then you would have to use the other definition. So that was minus sigma minus omega n plus or minus omega n square root of zeta squared minus 1. Because in this case, zeta is going to be greater than 1. P1 and P2 alone, again, forgetting about the other poles, but P1 and P2, if they were the only poles, so if the system was a second order system, the system would be overdamped because P1 and P2 are both real. All right, with that being said, I'll stop here for this part, and then I'll see you in part 2, where we will be talking about system stability. So see you there.